Hello, so today we're going to be juggling a few tasks. So task number 1 that we have for this assignment is drawing an example of a chiral compound. Now what the heck is a chiral compound? Chiral compound or chirality means it's a property of symmetry that its mirror image is non-superimposable. So here I am just going to draw an example for you. Here's the parent, and then I'm just going to draw a few hydroxides. This one's going to be on a wedge, this one will also be on a wedge, and then I'm just going to have between them on a dash of a hydroxide. Now, this is a chiral compound, and we are going to label it chiral compound A, or just think of it as compound A. But this is chiral. And by doing so, we can look at, So now we are going to do the second part of this task actually is to get the enantiomer. So by doing this, we can see we have to draw its mirror image. So when we do the mirror image, this also actually proves that it is a chiral compound. So by doing this, all we do, so this is not flipping, it's just reflecting. So same situation, the hydroxides will be in the same spot, it's just that long carbon chain is just going to be not rotated, but reflected. So our step 1, here we have drawn an image, a mirror image to help out to see what I mean. Now, step 2 of this, drawing the enantiomer, and we're also going to call this B, we want to redraw B by flipping it. So flip, when I mean by flip, it's going to look like A, the original compound. But when flipping this 3D structure, this also means it will change. So also another definition for a stereoisomer, a type of enantiomer. An enantiomer is a type of stereoisomer. So here I am, it's just going to flip it. So I flipped B back, so it looks like the original. But think of it as take your right hand and point your thumb at you. Your other fingers are just pointing up, but if you were to flip that hand towards your left, the thumb is behind. So when flipping, our wedges become dashes, so they are going to be turned away from us now. And our dashes are going to be wedges turning to us now. So, to double check, we know an enantiomer is a mirror image that is non-superimposable, meaning not the same. Furthermore, when we redraw B, and here I'm just going to show you that chiral compound A, and then this is the enantiomer of that compound. We just redrawed B to help it out, and you can really see that this is an enantiomer of each other. Here I am just writing some little notes to better understand this. Now, if I were, I'm going to show you why. A little more helpful. So if I were to take this compound and slide it over it, it looks the same, but it's not. The 3D perspective of it is completely different. That's exactly what a stereoisomer is. They are same connectivity, same molecular formula, but the 3D of it is completely different. The 3D shape is different. But yes, there we go. So think of that hand little motion that I just talked about. Now, let's move on to task number 2. In task number 2, we're going to be covering diastereomers. So we'll use the same-ish compound from task number 1 for our chiral compound turning in an enantiomer, but just a little differently. We'll use the same amount of carbons in that carbon chain. So here I am just going to redraw it, but I will have 2 of those hydroxides up here on wedges, and then in the middle I'm just going to do a wedge. Now, diastereomers are also a type of stereoisomer, configurational isomer. So diastereomers are not mirror images, but yes, they are superimposable, meaning they are not symmetrical. So this is the biggest difference with enantiomers and diastereomers. Enantiomers is a mirror image. Diastereomers is not a mirror image. We'll call this compound C. Now, this will be compound D, so draw the same thing. Remember, no mirror images. I'll do the same two hydroxides, but this will be a dash. This is where we compare what is the same and what is different. So here I'm just writing some quick little notes so we can answer this question. So looking at these two compounds, again, remember they're not mirror images whatsoever, and they are non-superimposable. So all these hydroxides, when you compare, they're the same, right? These upper two hydroxides are pointing out at you. But if we move on to these bottom two, they are different. Yes, they are. One is pointing out at you, and the other is pointing away from you. There is a difference in the 3D. So this is diastereomers because this is a type of stereoisomer or configurational isomer, and they're not mirror images of each other. And we can classify this as a type of isomer simply looking at the bonds and its 3D orientation. Only some chiral centers get reversed. Some must stay the same in order to be a diastereomer. Let's move on to our next task. Just give yourself a little more of a look. So, task number 3, we're going to be going over a miso compound. Not like miso soup, but miso. Okay, so I'm just going to draw an example of one. I'm going to do a cyclohexane, so here is going to be my hexagon. And I'm going to draw a wedge up here, a dashed hydroxide, and then another wedge right here. So, this is a miso compound because there are 2 or more chiral centers and it has a plane of symmetry. This makes it chiral. That's just a simple definition of a miso compound. So there must be chiral centers and there has to be a plane of symmetry. So I'm going to use this color red, make a line. Oops, sorry, little mistake there. Let's just erase that, go back to my pencil. There we go. Okay. So here I am just drawing that line of symmetry. And if you look at these two quadrants across from each other from this line, they are completely the same. Nothing is changed no matter what way you look at it. Completely the same. Okay. Not to confuse you, not to kind of jumble it up, but I'm going to draw an example of one that is not a miso compound, just for reference. So I'm going to do the same cyclohexane. There we go. I'll draw that wedge up there, draw a dashed hydroxide, and then where that wedge once was, it's going to be a dash now. Now, same kind of, situation. I am going to grab that red color to show you that this is not a miso compound due to its non-symmetrical status. So here we go. Here's that line. If you look, there's a dash and there's a wedge. Difference in 3D, it's not the same. There is no plane of symmetry. So very key, it must have a plane of symmetry to be a miso compound. Okay. Now, let's move on to our next task. This task will be a little larger, has more steps, and this is where we're going to determine whether a compound is an R or an S configuration. Now, let me just draw the compound that was given. So here I am just drawing the structure. Now, the first step of this whole situation determining configuration is where the heck is the chiral center? So I'm going to use this purple pretty color to circle it. Now, how did I know that? How is this a chiral center? A chiral center, think of it as either sp3 hybridized or it's a tetrahedral geometry, and it has to have 4 completely different things bonded to it. So say I had 2 hydrogens here, that would not be a chiral center. So 4 different things are bonded to that carbon in that center, in our chiral center. Here I am just writing a few notes to remember that. And that was step 1, determining our chiral center. Okay, now step 2 of this is to list our groups that are attached to our chiral center. So by doing so, we can start easily with our oxygen on our dash. So don't think of that ethyl group that comes after it. It's just the oxygen that's technically bonded to that middle carbon. So just think of it as that way. So we have oxygen as one of our first groups. Then I'm going to kind of color code so it's a little bit easier to see, but then we have a hydrogen. I'm going to kind of draw a triangle around that. That is another part of our group. Then let's do this ethyl group right here. Now, don't go to where there's a carbon and then there's 3 hydrogens. We're looking at the center one, so it's going to be that carbon is attached to another carbon, but within that carbon you have 2 hydrogens. That is what an ethyl group is. Okay, now for our final and only, we have this oxygen, carbonyl, C double bond O. So we're going to draw that carbon because that's what's attached to the middle, and we are going to treat the double bond as 2 singles. That's kind of what it is, but for our case scenario, just treat it as 2 singles. You'll just see it a lot better. So these are our groups. Now let's prioritize them. By prioritizing, I mean that we want to prioritize out the highest by atomic number. So number 1 will be the highest, number 4 in our case is the lowest. So hydrogen is the lowest of an atomic number of 1. So that's out of the way. So what would be number 1? Well, that would be our oxygen. Not the C double bond O, but just oxygen because it has a higher atomic number than the rest of them. And we're just going to go down the line. It's like alphabetical order. O, H, and then we have 2 C's. So this will be number 2, and this ethyl will be number 3. Why? Well, 2, like you see I have circled, the oxygens are a higher atomic number than H. It's almost like you prioritize A over B because A comes first and then B. Same thing. Oxygen has a higher atomic number than H. So we have this. Now our next is we label. This is step number 3. So hydrogen is 4, oxygen 1, our ethyl will be 3, and that O double bond will be 2. We run into a problem because if we want to kind of set it up via arrows, we're going to be all jumbled up. And what we want now, so we want that hydrogen in the back. We want it on that dash. By doing so, we can now rotate the bond. But remember, we are only rotating the bond in the chiral center because that double bond oxygen, we do not want to touch that. Do not touch that. So we're only rotating the carbon at the chiral center so hydrogen can get the place of going in the back. So I'm just going to redraw this to the structure so you can visually see what the heck I'm talking about. Here I'm just making sure I'm drawing it correctly. Double bond O. Then let's draw that ethyl group pointing out. And then dash oxygen, ethyl, there we go, and then hydrogen, can't forget it. So what I mean by this is that where I have labeled, that is the one and only carbon that we are going to be rotating. This is the center that we rotate. This, don't touch it. Don't worry about it. It stays at number 2. It is still ranked number 2. Don't touch it. We don't want to worry about that. Okay, let's completely redraw this whole thing. Oops. There. This is what I mean. We rotate it up. because if we were rotated the other way, kind of backwards, hydrogen would be in the ethyl spot. So hydrogen gets the spot of oxygen, oxygen gets the spot of the ethyl group, and our ethyl moves to where our hydrogen is. Let me show this. Okay, so redraw the structure. And it'll look a little like this. So remember, we are moving that hydrogen to the dash. Oh, let me just change color so it's all the same. Get my black pencil out. There we go. That will be our H. Okay, here's our ethyl. I'm not gonna draw the ethyl in, because remember, we are rotating all of them. They are going to be in different spots. Here's the dash. Remember, this double bond oxygen stays the same. We don't worry about that. Oh, let me draw that double bond a little better. We don't worry about that side. So, okay. Now, hydrogen is going to move where the oxygen was. Remember, we are rotating up. So hydrogen is now in the back. Where hydrogen was, this is where our ethyl is. I'm just going to label it so you can see it, and it's just not a random line. And this is where oxygen with its ethyl group pointing out. There you go. Now we can prioritize and label properly. So we're going to use the same chart, the same prioritization that I have done here. So I'm just going to circle all of that, copy it, use the same exact thing. Hydrogen is still 4, that oxygen is still 1, that double bond oxygen will be 2, and our ethyl is still going to be 3. Prioritization still stays the same. The only thing we changed is how the structure looks like. So as we rotate, like I said, the carbon at the chiral center has hydrogen now where oxygen was going away from you. So if we label this with arrows, you can see it's not jumbled up. 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 circles back to 1. Now, the direction is pointing left. So this means we are going counterclockwise. And counterclockwise, we are talking about an S configuration. So that is our answer. But if it was going to the right, so if the arrows were pointed the other way, that would be clockwise, meaning it's a 50-50, so it would be an R configuration because it's going right for R. So here's just some little notes. S, it's going to be S. Counterclockwise means it is an S configuration. I'm just going to draw a really big S so you can really see what I mean. There it is. This is an S configuration. And there we have it. That is our answer.